Hello. All right, so welcome everyone to the second to last day of the conference. So today is the gauge theory day, and we're very pleased to have Peter Kronheimer, who will tell us about gauge theory and low-dimensional topology since 1982.
So thank you very much. It's a pleasure and an honor to be here to give this talk. My subtitle is a panorama and a survey of some themes. Fortunately for me, this is the fourth panorama talk, so you're familiar with the basic definitions of panoramas and main results. I just have to tell you what the themes are here. But before that, I want to briefly tell you what gauge theory is. So gauge theory means many things depending on who you are. For me, it means the self-dual Yang-Mills fields taken in the setting of differential geometry. We have an oriented Riemannian four-manifold. You can think to start with the just Euclidean four space, which is certainly where the subject started. If you want something compact, think of the four-sphere, complex projective space. Later, we'll be talking about complex algebraic surfaces, so think perhaps of a smooth surface inside complex projective three space, thought of as a smooth four-manifold. The other ingredient is a principal bundle with structure group, some Lie group G, over this four-manifold X, and G will be the simplest Lie group nearly all the time, the group SU2 for us. On the bundle, we want a connection, which I'll denote by A, and its curvature, which is F. Locally, A is a one form, and F is a two form. In the setting of theoretical physics, I'll say a tiny bit more about this later. X might be space-time, but here made Euclidean. A might be referred to as the gauge potential or the Yang-Mills potential, and F the Yang-Mills field, its exterior derivative. But returning to differential geometry, as a two-form, there's an operator which we can make act on the curvature. This is the Hodge-Star operator. It maps two forms to two forms. And we say that the Yang-Mills field is self-dual if star F is equal to F. As an equation for F, this is just a simple linear constraint, but F, it's A, the connection, we should think of this as an equation for. And F, in terms of A, involves the derivatives of A and a quadratic term. So it's a partial differential equation for A. It's a first-order equation, in the sense it involves first derivatives of A, but it's a nonlinear first-order equation because quadratic terms appear in the expression for F. So we say that F is self-dual, or with an abusive notation, we perhaps say A is a self-dual connection on the four-manifold if this equation holds. The structure group, as I said, will be the Lie group SU2 most of the time. It's great that the language of connections, curvature, and differential geometry allows us to write the equation just star F equals F. And that's how I first saw it, and I had heard of this work of Simon Donaldson when I was a finishing undergrad, and I went to the library and I tried to figure out what this equation really was in terms of A, and I thought it was going to be important for me to write this down in terms of all the equations, all the components of A. I did that, and then realized it wasn't important at all for me to do this, at least not at that stage in my life. So this is not important at all, but that's sort of what the equations sort of look like for 12 functions of four variables and 9 equations for them. Back to a little bit of the history. So we're going to be interested in finding solutions to these equations, initially on four space, R4. And the people who went looking for solutions were theoretical physicists paper by Polyakov and a follow-up paper by 4 authors gave the first interesting solutions to these equations on Euclidean force space. This is Polyakov's paper. He's coming at it as a physicist. Infrared catastrophe up there. He promises in this paper to actually give us a solution in a follow-up paper. That follow-up paper is this. It's by Belevin, Polyakov, Schwarz, and Tupkin. In this paper, BPST, the authors, they write down this solution, which I've drawn a picture of here on R4. It's got various names. It's the standard charge 1 instanton, or it's the BPST solution. What I've drawn there is a sketch of the size of the curvature as a function on R4, and it's sort of a single point in space-time of concentration there. The equations are conformally invariant, so we can also look at this as essentially the same solution on the 4-dimensional sphere, adding a point at infinity. Shortly after this, solutions of higher charge were found. So that BPST solution is a sort of charge 1 solution. De Hooft found a family of solutions of higher charge, unpublished at the time. The first published formula for higher solutions was actually published by Ed Witten in the 70s. So that's a sort of charge 2 solution, which you could find in Witten's paper. De Hooft's solutions for charge K involved roughly 5K parameters. And perhaps it wasn't initially clear whether these were the general solutions or not. Atiyah, Hitchin, and Singer in this paper applied the index theorem to figure out what the number of parameters of the general solution should be. And for charge K, they came up with the answer of 8K minus 3, meaning that de Hooft solutions are not the most general. The search for the general solution in any form was made possible by work of Richard Ward. He was a student of Roger Penrose. Penrose had this twister program at the time which tried to interpret the equations of mathematical physics in terms of complex geometry. And Ward's correspondence was a sort of instance of that general plan, and he interpreted the self-dual Yang-Mills equations in terms of complex geometry on the complex projective 3 space. That opened up the possibility of understanding the general solution using algebraic geometry. This is a paper of Atiyah and Ward where they give a general construction, general enough to produce all solutions in terms of algebraic data on the complex projective 3 space. This was a predecessor of what later became called the ADHM description. This period of sort of geometry, studying self-duality for its own geometrical sake, sort of culminated perhaps in this paper of Atiyah, Hitchin, Singer, where this lovely survey, they bring together some index calculations which I referred to, Penrose's twister ideas, the Ward correspondence, and many other aspects of index theory and topology and geometry in that paper. This is just an anecdote here. We call these things instantons. De Hooft wrote a very readable paper based on a lecture he'd given in 1994. It's a great read, and he explains that he introduced the name instantons. But his choice of word was censored by Physics Review letters. They wanted to change it to Euclidean gauge pseudoparticle solutions, EGPS for short. When I protested, he writes, they went as far as Euclidean gauge solitons, and these ugly acronyms only hastened the general acceptance of instanton ever since. So if you like that anecdote, you should go to Hoof's paper and find more good stuff. So this was from theoretical physics to geometry, perhaps culminating in the Tirichin-Singer paper. There's another sort of aspect to this which is less geometrical. We can study, and these are a partial differential equation. We can think of this in more PDE terms. Around about 1980, plus or minus, two important contributions were made in this direction. One was Uhlenbeck's compactness theorem. If I have a sequence of solutions to these equations, is there a convergent subsequence? And Uhlenbeck's answer was basically yes, except for a phenomenon which she allowed us to understand very well, which was this bubbling phenomenon, just that pseudoparticle, that blob there, can get more and more concentrated, and the limit does not exist as a smooth solution. That phenomenon she analyzed, and we now understand that that's the only sort of non-compactness in these moduli spaces. The other important contribution came from Cliff Taubes, who found a technique to establish existence. So the Ward correspondence applies to solutions on R4 or S4 or a few other manifolds, but always in a very geometrical context. If I give you a general Riemannian closed form manifold, it's not clear any solutions exist. Taubes answered that question initially in a restricted case and then quite generally on form manifolds. His technique of constructing these is now called gluing. These two things together open the door to studying the moduli space in general. So for Riemannian manifold X compact, we can study the moduli space of charge K instantons on X, the space of solutions up to isomorphism. That was where things stood when Simon Donaldson wrote his PhD thesis, which you can now download from Oxford's archives. Donaldson's thesis is very famous, but what we actually know most is chapter 3. There are two notable things about this thesis beyond the extraordinary mathematics in chapter 3. Those two notable things are, this was written in 1982, and he finished his undergraduate career in 1980. The other very notable thing is that this is chapter 3. And if you haven't thought about it before, you should ask, well, what's in chapter 1, 2, and 4? And chapters 1, 2, and 4 open up a whole other new avenue which became very important in mathematics, and that's the study of the Kobayashi-Hitchin correspondence, which he was really the first person to study from a PDE point of view. And in his thesis, he sort of solves that problem in some important special cases and opens the door to his later work, which solved it in general. It's also related to his considerably later work on Kähler-Einstein metrics. So zooming in on chapter 3, the homotopy type of a compact, simply connected oriented form manifold is determined by the intersection form. This is the quadratic form on this integer second cohomology given by the cup square. And this is theorem 1, very famous theorem of Simon Donaldson, which says that for such a smooth oriented simply connected manifold, if the quadratic form is positive definite, then that form is diagonalizable. The matrix of that quadratic form is the identity matrix in some basis. The special case of that, for example, what is that telling us? It's telling us there's various things the quadratic form cannot be. In particular, it cannot be a direct sum of copies of the E8 quadratic form, a definite form which is not diagonalizable. This is a sketch of the proof, not quite in historical context, but perhaps a modern rephrasing of it. We put a generic Riemannian metric on the four manifold, and we consider the moduli space of charge 1 instanton solutions. From the TH and Singer paper, we know this is a 5-dimensional manifold. That's an index calculation. An index calculation for families tells us this moduli space is orientable. Uhlenbeck and Taubes together tell us what it looks like at its boundary, and they tell us that it can be compactified by adding a copy of the original four-manifold X as a boundary. At this point, our four-manifold is the boundary of a smooth five-manifold. Any four-manifold which is a boundary has 0 signature. The signature is a cobordism invariant. So it follows that quadratic form has signature 0. But that quadratic form has signature 8m, that Q up there. So m has to be 0. I do this picture once in a talk in the 80s somewhere, and someone in the audience raised their hand and said, what about the cones on CP2? If you're an expert in this, you'll know what that means, but I'll come back to that. I promise to come back to that later. I tell my algebra students, every proof is a proof by contradiction if you want to phrase it that way. You just start by assuming your theorem is false. And when you've proved it, that's a contradiction. The Donaldson's theorem, I mean, you don't have to phrase it that way either, but it's quite naturally a proof by contradiction, the way you want to, as a story. And that also applies to some things which came very shortly afterwards. He strengthened the result to prove certain other quadratic forms do not arise. These are simple, a couple of indefinite quadratic forms can't arise in the same sort of situation. Again, proofs by contradiction, considering moduli spaces of instantons. There are various other things you can try and do in a sort of similar proof by contradiction idea. Four manifolds with group actions were briefly studied. It turns out that I think a lot of these results could be proved without gauge theory. But if I have a group action, say a finite group action on a four manifold X, can it have just one fixed point? Well, an idea to work with is, well, if it did, then perhaps there's this moduli space on which the group acts, and one fixed point on the boundary, and maybe a one-dimensional fixed point set in the interior. A one-manifold can't have just one end. That question mark up there means something else has to happen to that fixed point set. It has to land up at some other fixed point on the boundary. So the group action on X has to have another fixed point somewhere. This idea that one-manifolds can't have just one boundary point is the key to understanding a lot of proofs in this subject. Slightly more sophisticated, well, a lot more sophisticated than the naive sketch I've just given for the group action case, concerns the homology cobordism group. I want to tell you what that is. A homology three-sphere is a three-manifold whose homology is that of the three-sphere. The Poincare homology sphere is the first example which isn't S3. And two such are homology cobordant if there's an oriented four-manifold with boundary, whose boundary is a difference of y1 and y0, a cobordism which has the homology of a cylinder, just the same homology as the trivial cobordism from S3 to itself. This is an equivalence relation on homology three spheres. The equivalence classes form a group, and that's the homology cobordism group, theta 3. You can directly deduce from Donaldson's first theorem that certain three manifolds, homology spheres, are not homology cobordant to each other. But it's rather limited what you can do directly working with those theorems about closed manifolds. Opening the door a lot wider was work of Fintershell and Stern. I want to illustrate some of their ideas in a particular example. 2317 and 51349 are two Boris-Scorn homology spheres. You don't really need to know what they are. There's some of the best understood homology three-spheres. What you can do with a three-sphere, homology three-sphere, is study the Self-Yang-Mills equations on a cylinder, R times the three-manifold. So this is a three-manifold Y multiplied by the real line. We look at solutions of these equations. That sort of pink stuff there is supposed to indicate where the curvature is actually happening. As you approach the ends, the connection becomes flat, which means it becomes a possibly trivial, possibly non-trivial representation of the fundamental group, a flat connection on the two ends there. It's an important fact, not particularly relevant in my exposition, that this is the descending gradient flow equations for functional on Y itself, thinking of the R coordinate as time. Functional there being the Chern-Simons functional. So that's sort of curvature heat map, that blob. So why are these two manifolds not homology coordinate? Again, it's going to be proof by contradiction, and it's going to involve a one manifold. If we look at 2317, Finchel and Stern learnt that there's a solution on this cylinder which is flat and non-trivial at one end and flat and trivial at the other end, and has got action 0.010 to 3 significant figures. 51349, very similar story, but the action's a bit bigger, 0.011 to 3 significant figures, strictly larger than the other one. In the middle now, we're supposing there's a homology cobordism between these two manifolds. And we put one half cylinder on the other end, one half cylinder on the first end with these two different homology spheres. And using techniques which you can think of as cousins of Taub's gluing theorem, the existence of the solution on 2317 means that we can construct a solution which is flat and non-trivial at this end, starts to become trivial at this end, and stays pretty much trivial all the way along. But there should be at least a one-parameter family of these, because where that curvature heat map has its center of mass can slide off to the left. So there's one end of this one-dimensional moduli space of solutions, and there must be another end. And there's pretty much nothing it can be except some solution where the curvature drifts off down the tube to the right. As that curvature blob on the right goes down there, we essentially get a solution on the cylinder on the right, but the smallest energy of any solution on the right is 0.011. In this family, the action is constant. It started off as just 0.010. There can't be any solution with action bigger than that in this family. The fact that 0.011 is bigger than 0.010 is the contradiction here. There can't be this homology cobordism in the middle. They went further. They and Furuta proved the three-dimensional homology cobordism group is not finitely generated. Prior to Donaldson's work, it was possible the homology cobordism group was just Z-mod 2. There was just the phi sphere, the Poincare homology sphere, and everything was homology cobordism to just at least one of those, exactly one of those. This idea of measuring the change of the Chern-Simons action 0.010 has been extensively developed since. I mentioned there some of the people who've done important work using this idea of the Chern-Simons filtration. It continues to give back new results in mathematics here. Leaving aside proof by contradictions, themes 2 is invariance of manifolds. Rather than look at the self-dual connections, let's just look at all the connections on our four manifold in this principal bundle. That's some infinite dimensional space. I've called it C. It's a space we understand quite well. What we don't understand so well is this solution set to the self-dual equations. It sits inside there as a distinguished finite dimensional subset. The big space, the green Dello cube, has a cohomology ring which we completely understand. It's the graded symmetric algebra on the homology of X. We can evaluate those well-understood cohomology classes on the fundamental class of this modulo space M. It yields for us a map from the cohomology ring to the rational numbers. That cohomology ring being well understood, this is a map from polynomials in the homology of X to the rational numbers. And this is Donaldson's polynomial invariant. There was a predecessor to this invariant, which I'll be slightly historically inaccurate in passing over. This invariant can distinguish smooth structures on manifolds which are homeomorphic. Excuse me. So, in particular, it established the existence of exotica in dimension 4. I don't know if you can read that small print. I can't read with my long-distance glasses on what it says here on the screen. I hope it's not too small. Donaldson proved some remarkable facts about this polynomial invariant. In general, it's non-zero if X is a complex algebraic surface. By contrast, it's zero if X can be written as a connected sum in an interesting way. Combining those two tells us that complex algebraic surfaces, for example, the quintic surface in CP3, it can't be a connected sum of, say, copies of CP2 and CP2 bar. Since there's a manifold homeomorphic to the quintic surface, which has that connected sum decomposition, it follows that the quintic surface, for example, is exotically related to a connected sum of CP2s and CP2 bars. So this initial application in the paper on polynomial invariants has its origins in about 88 and published, I think, in 1990. Didn't contain calculations. There was a previous work of Donaldson which studied the so-called Dolgochev surfaces. The calculation for some explicit complex surfaces were done by, first by Donaldson. There was a paper by Kotchik on the Barlow surface. Calculations of Donaldson invariants in a non-complex algebraic setting were done by Gomp and Mrowka. The Donaldson invariants were strong enough to completely classify smoothly the regular elliptic surfaces. There's people who contributed to this along the way. Friedman and Morgan there get the credit for writing an expository book which tells us the complete story there. These polynomial invariants are there's apparently a lot of data in them. There's the instant number k and a polynomial which grows in degree with k. An abundance of coefficients there. How much data is there? With Tom Mrowka in 93, we proved a structure theorem which sort of shows how much data is really sort of free data in the polynomial invariants. This was proved for four manifolds of simple type. I'm not going to talk about simple type except that it's actually an open question whether all four manifolds have simple type or not. The third theme is the study of embedded surfaces in four manifolds. If I have a smooth four manifold and an embedded surface smoothly embedded in there, there are two numbers I'm interested in. One is its genus, and the other is its homology class in H2X, the fundamental class of this oriented surface. And there are sort of there's a theme here, which is that embedded surfaces constrain the Donaldson invariance. So by the same token, the Donaldson invariants constrain embedded surfaces. How did that play out? Constraints for the existence of embedded spheres representing particular homology classes were pursued by Danny Ruberman. Spheres and tori, embedding those was obstructions were found in work considerably more technical by Morgan, Wuffer, and Ruberman, who published results as a monograph. Constraints for higher genus surfaces were proved by myself and Tom Mrowka using a slightly different technique of singular connections. Applications of these singular connections included the first bullet point there, which is that there's a very general inequality between the genus and self-intersection number for four manifolds of simple type with non-zero invariants. The genus and the self-intersection number are always related by that inequality. That's strong enough to prove what's called the local Thom conjecture. It tells us the slice genus of torus knots and the unnodding number of torus knots. And it led to this structure theorem, which I referred to earlier. It threw out some classes, the basic classes, which you should think of as counterparts to the canonical class of a complex surface. That inequality 2g minus 2 greater than or equal to sigma dot sigma, it's a pleasure to acknowledge that that is jotted down in my lecture notes as a conjecture from a lecture which John Morgan gave at Princeton when I was at the institute there, I think. I may have the timescale slightly wrong. Talking about the Morgan, Wufka, Ruberman results and speculating about the generalizations. Also speculating, I think, that the canonical class should be something that you can just define differential topologically using Donaldson invariants, which is somehow borne out in these basic classes. A quality of this work is that smooth algebraic curves are genus minimizing. We didn't prove that in a general setting, but for example, that's true for smooth algebraic curves on a smooth quintic surface, for example. Singular connections I won't say much about, but these are connections with codimension 2 singularities. If I have a codimension 2 locus inside a four manifold, I can consider connections which don't extend across that codimension 2 locus because their monodromy around the link of that two-dimensional surface is non-trivial. If you fix what you want the monodromy to be, it turns out there's a new moduli space you can study of such singular connections. You can interpret these as orbifold connections if alpha is a rational number and you work with the geometry suitably. I'm not going to say much about Floer homology, but I'm going to say a little bit about here. We've seen this picture before. This is an anti-self dual connection on a cylinder. It's a flat connection A at one end and a flat connection B at the other. And I mentioned that the equation is a gradient flow equation. So you can think of this solution as a path in the space of connections on Y. As such, it's a gradient flow line from a critical point A to a critical point B. And you can do Morse theory. A and B are generators of a complex, and these trajectories are the differential. This was Floer's definition of the instanton homology of Y, initially in the case of a homology 3-sphere. There are many variants of this. Floer proved a surgery exact triangle, which we heard mentioned yesterday in Peter's talk. Instanton homology is, can be shown in some cases in its generalizations to other manifolds to be non-vanishing. The general results there were proved sutured manifold techniques. I'll come back to those briefly when we talk about Seiberg-Witten for homology. And there's a relation to the fundamental group because of the flat connections that appear as A and B. It's also related to Havanov homology via a spectral sequence, which makes it attractive. So that surgery, that was the first surgery exact triangle. The non-vanishing result, that was proved by Tom and me, and once we knew what we had to do, there was just a clear model for how to proceed, and that was in similar results which have been developed in Heegard flow homology, most completely by Andras Juhas. The relation to the fundamental group led to a proof of property P for knots, and applications to SU2 representations, more recently on surgery on 3 manifolds. The relation to Havanov homology led to a proof that the Havanov homology detects the unknot. Kim Freushoff used the Yang-Mills invariance to define the first non-trivial homomorphism. But Finstein and Stern has shown that the homology cobordism group is very non-trivial, but the rational numbers is a rather non-trivial abelian group, which does not omit any homomorphism to the integers, non-trivial. The first such homomorphism was conducted by Kim Freushoff using instanton homology. A corollary of his work, just illustrative, if you take 100 copies of the Poincare sphere, the Poincare sphere bounds a manifold with intersection form E8. So 100 copies bounds a manifold whose intersection form is 100 copies of E8. You can ask what other quadratic forms arise from 4 manifolds with the same boundary, in particular which negative definite forms can arise. And Freushoff proved if there were 100 negative, if there are m summands in the quadratic form of a 4 manifold with boundary, the given 3 manifold, then the number of summands m which are non-standard has to be at most 100. I think we might hear from Ali later this afternoon of more modern applications of instanton homology and Freushoff type invariants. Another theme is diffeomorphism groups. Gauge theory lends itself to the study of families. Naturality in families is sort of built in some sense, to the constructions in gauge theory. But it was a while before this was realized in new results in mathematics, and that began with Danny Ruberman's paper in 1998. Here's a particular 4 manifold in his application. K3 connects a CP2 and then 2 oppositely oriented CP2s. He showed that the mapping class group of this smooth manifold contained elements which were non-trivial smoothly in the mapping class group, but put into the topological mapping class group were topologically isotopic to the identity map. Okay, so that's 3/4 of my talk, and I've just done part 1. Part 2 is the Seiberg-Witten equations. This is a paper by Seiberg and Witten, which doesn't actually contain the Seiberg-Witten equations, but if you read it right, it tells you that Donaldson theory has a cousin. Witten explained this to us in a paper in 1994, Monopoles and 4 manifolds, where he did write down the Seiberg-Witten equations, told us how to make new invariants of 4 manifolds using them, and proved all sorts of interesting stuff about these new invariants. In the same volume of math research letters, there's a paper of Tom and myself on embedded surfaces into the projective plane, proving the Tom conjecture for CP2. I'll return to these themes. There's a paper by Cliff Taubes on the connection between these Seiberg-Witten invariants and symplectic forms. What are these equations? X is going to be a Riemannian manifold. As in Witten's paper, I will simplify my life by saying it's a spin manifold. You don't really need to know too much about spinners, though. The data will be this X and a line bundle on X. And these equations are not just for a connection, they're for a connection and a spinner. But the connection now is just a unitary connection in a line bundle. It's an abelian thing. It's basically just a one form. The L-valued spinner phi enters non-linearly with cross terms between A and phi and phi and phi. The first equation there is just a Dirac equation for phi coupled to the connection. The second involves the self-dual part of the curvature. So A is an abelian connection. There's no Uhlenbeck bubbling here. The compactness results of Uhlenbeck were sort of compactness modulo bubbling. For the Seiberg-Witten equation modulo space, the solutions are compact modulo nothing. They're just compact. That was immediately appealing to anyone who'd worked hard with the non-compactness that's present in the Donaldson modulo spaces. The first sort of themes here were just simpler proofs and stronger results, the things which had been trying to prove and were getting perhaps closer to with the Donaldson invariants. They all just kind of fell over with the Seiberg-Witten equations. The same sort of proofs by contradiction were sort of redone with the Seiberg-Witten modulo spaces. This was the Yang-Mills modulo space, the proof in Donaldson's thesis. There's a similar looking proof using the Seiberg-Witten equations that sum of E8s quantifies as the intersection form of a closed manifold. But it involves a modulo space which essentially looks like that. That boundary point there is not a bubble anymore. It's just a solution with extra symmetry. It's a reducible solution to the equations. So a lot of things happened very quickly for old problems which were once thought about with the Donaldson invariants, but now could prove with the Seiberg-Witten equations. The invariance of the canonical class up to sign for an algebraic surface under diffeomorphisms was quite straightforward to prove. The invariance of Kodaira dimension and the plurigenera, so concepts that come from algebraic geometry of algebraic surfaces turned out to be diffeomorphism invariants. The embedded surfaces problems was completed in much greater generality. I mentioned the case of surfaces in CP2. General algebraic surfaces and curves with positive normal bundle were also sorted out quickly. Curves with negative normal bundle had to wait a little bit longer. But these was kind of all proved within, I mean, it'd be an exaggeration to say 24 hours, but it kind of almost seemed that way at the time. Just as we have the instanton homology, there's a Seiberg-Witten Floer homology constructed in a very similar manner. The Seiberg-Witten Floer homology again detects the genus of knots and encodes the Thurston norm of three manifolds. First proofs of these things actually involved symplectic topology and predated the instanton results, which relied on the work of Juhász and others. But these were sort of themes which had been around and expected, and now we could just prove them more quickly or prove them at all. What was new with the Seiberg-Witten equations, as far as new ideas and applications, are a few. One is the idea of finite dimensional approximation, which originated in work of Furuda. You take these infinite dimensional equations, basically now equations on a linear space of spinors and one forms, and you sort of approximate them finite dimensionally. He greatly strengthened the results on quadratic forms from Simon's thesis. If the quadratic form is n copies of the hyperbolic and m copies of E8, then n must be bigger than m. That's Furuda's so-called 10/8 theorem. 11/8's conjecture is that n must be at least 3/2 times m. That's still an open problem. Bauer and Furuda took this finite dimensional approximation idea and did some very cool stuff with it, defining refined invariants of four manifolds. An example application is that if you take a connect sum of 2 or 3 K3 surfaces, then it's still true that embedded surfaces satisfy this inequality, 2G minus 2 greater than or equal to sigma dot sigma. Something which is notable because such a connect sum has trivial Dons invariants and trivial Seiberg-Witten invariants in the traditional sense. Finite dimensional approximation was also relevant in the three-dimensional setting. Again, replacing this infinite dimensional gradient flow by a finite dimensional one. Chip and Manolescu defined the Floer homotopy type for homology 3 spheres, replacing Floer homology via Conley index theory. Conley index theory is a much more flexible tool than Morse theory, and it eased the study of group actions on 3 manifolds. That's a sort of external symmetry, and also incorporating the internal symmetries of the equations themselves. So an application of those internal symmetries was in the work of Manolescu, defining new invariants on the homology cobordism group, gave rise to a proof that some higher dimensional manifolds in dimension 5 and up are not homeomorphic to simplicial complexes. This settled an open problem that went back basically to the fundamental ideas of what is a manifold in the 50s. Another thing that can be done with extra symmetries is incorporating real structures. Real Seiberg-Witten theory has seen recent applications. This is combining an external symmetry of an involution on a manifold with an internal symmetry, which is complex conjugation in the equations. You can think of it as a tool to study manifolds with involution, or via branch covers, you can think of it as a tool to study, for example, 4 manifolds with embedded surfaces. So a very notable application of that is the result of Miyazawa, that there are exotic embeddings of the real projective planes in 4 space. Diffeomorphism groups also have been, the work of Danny Ruberman has been sort of followed by considerable applications using Seiberg-Witten theory. In Danny's talk, Whose talk? Dane Twist's? I can't remember. It's also some of these have appeared previously in our lecture series. Many results with many authors applying the Seiberg-Witten equations and Seiberg-Witten equations of families to study exotica in the diffeomorphism groups. And as has been mentioned before, there's quite disjoint work on diffeomorphism groups now, which is from Watanabe, Gabai, Gay Hartman, and others. where the fundamental ingredient is configuration spaces of points, and in Watanabe's case, of conservatory characteristic classes. Interesting to know whether there's any connection there at all. Another theme is connection to Riemannian geometry. Solutions to Seiberg-Witten equations, they interact with the scalar curvature of a manifold. There are none if the scalar curvature is positive. They also interact more subtly with the Weil curvature of a four-manifold via Weizenbach formula for two forms. The scalar curvature applications were sort of immediate. Prior to Seiberg-Witten, we knew very little about this. From what we knew in higher dimensions, it seemed possible that every simply connected four-manifold had a metric of positive scalar curvature if just one obstruction vanished, and that obstruction was the signature in the case of a spin manifold. But after Seiberg-Witten, it seemed possible, this is not completely borne out, but it seems possible that the only simply connected manifolds with positive scalar curvature in dimension 4 are kind of the obvious ones. In particular, a quintic surface in CP3 does not have a metric of positive scalar curvature. We know that now from Seiberg-Witten. Einstein metrics, this is application, illustrative example of Le Brun's work. Take a nice algebraic surface, degree 9 in CP3, blow it up 99 times. Le Brun says there's no Riemannian Einstein metric on that. We're not talking about Kähler Einstein here. This is not Kähler geometry. It's just a four manifold. Is there a manifold of positive scalar curvature? Sorry, a manifold satisfying the Einstein condition. It was previously known that you have to blow it up 225 times to contradict the Hitchin-Thorpe inequality, which is the only known obstruction otherwise. Do I have to blow it up 99 times? I don't know. I think it's an open problem. I think if you blow up that manifold just once, I think you can conjecture there's no Einstein metric. I think you can make that conjecture pretty much generally. No idea what the status of that is now or will be in 25 years. I asked AI to produce an image of a very, very large pile. It did the wrong thing. It produced a picture of a large number of copies of a small preprint. But actually, this should be something different. This should be papers, some of which are enormous. So there was a very short application of the Seiberg-Witten equations to symplectic geometry in the work of Taubes. Non-vanishing of the Seiberg-Witten events on symplectic four manifolds. A much deeper application came shortly afterwards, the relationship between Seiberg-Witten invariants and pseudo-holomorphic curves. This answered a question of Gromov eventually on the uniqueness of the symplectic structure on CP2. Closely related in dimension 3 is the connection between Seiberg-Witten flow homology and embedded contact homology, which is something defined on contact 3 manifolds, and the connection between that and Heegard flow homology. So that's another couple of very long stories in this field. I'm not going to go into this very long story, but this is a very significant part of the story. An impressive application of that was Taubes' proof of the Weinstein conjecture in dimension 3. This says that the ray vector field on a closed 3 manifold always has a closed orbit. This was a long-standing problem in Hamiltonian dynamics, which is still open for higher dimensional contact manifolds, dimension 5 and above. I promised actually to come back to cones on CP2. This is the picture which launched 1,000 workshops. if you're in the audience and you've had a birthday any time in the last 12 months, happy birthday to you. And that's the end of my talk. Thank you.
All right, are there any questions? Someone all the way in the back. Do we have a spare microphone? Or what, you? Okay.
Why were the physicists interested in those equations in the first days?
Why were those equations studied?
By the physicists.
By the physicists? And to some extent, there's an explanation in Polyakov and the predecessors of that paper. The Yang-Mills action appears for real in physics. It describes the strong interaction forces and the weak electroweak interaction. So it's part of physics, but studying actual classical equations of those zeros of those equations, or critical points of the action, is not immediately motivated by the actual physics, which is, after all, a quantum field theory, let alone studying them in Euclidean signature. But that, I mean, I'm no physicist, but that studying the critical points of the Lagrangian after putting it in a Euclidean signature is a standard way to begin to understand the quantum field theory. In particular, Polyakov explains in his paper, his motivation for this is that these critical points, the solutions of the classical equations, control long-range interactions of the forces described by the gauge theories. If you want any more with fewer ums and ahs, then you'd have to take a course in quantum field theory and then read Polyakov's paper, I think.
Other questions? Yeah.
I guess slightly naive question. The SU2 as a structure group is very much motivated from physics point of view. I get why physicists care about it. Why from mathematical point of view didn't we take something like much more natural? If we have a 4 manifold, then tangent bundle has an general SO4 structure group. What happens if we study SO4 Yang-Mills? Like, is it interesting, or is it trivial, or is it like analytically complicated or something?
And that's a good question. I think from the very beginning, when Donaldson invariants were defined using SU2, there was the thought, well, hey, what about SU3? And so on. Pragmatically, there's quite enough for us to do with SU2. There were technical difficulties, but perhaps not serious to overcome in defining Donaldson invariants for SUN, for example. You can do that. Nothing much has come for theorems of this sort by studying gauge theory for higher rank groups. You refer to actually using SO4 for the structure group. Thinking about Yang-Mills and thinking about Yang-Mills solutions as connections on the tangent bundle is a potentially interesting thing, which suggests coupling Riemannian geometry to the Yang-Mills equations. I think that's not something which I know of in the literature.
Okay, other questions? All right, if there are no other questions, let's thank Peter again. And And we will have the coffee break now, so let's meet back here in half an hour at 10:30. I guess we'll just start. For our second main talk, we have Tom Mrowka, who will tell us about knot homologies from the perspective of gauge theory.
Well, it's a big pleasure to be here. One of the great thing about working with Peter is that you get to work with Peter. The bad thing is that when you have to give a talk after him, I don't know. Anyway, here we go. So I want to tell you a little bit, kind of, in some sense, it follows up on Peter's talk. In fact, I was going to give a different talk, I thought, but then I thought I should give more of an overview. But it's sort of going to connect with some other themes that Peter didn't mention and focus in particular on knot homologies and a bit of the history there. Some of the history is wrong. I'll try and correct it along the way. But one of the interesting things that Peter didn't mention that it has a lot of influence on the area is this Yang-Baxter equation. And this is a page from Baxter's famous textbook, Exactly Solved Models in Statistical Mechanics. And there is the Yang-Baxter equation. And this is published in the 80s, early 80s, but I think the work was earlier. And this is Yang's 67 paper, where he's thinking about trying to understand interactions of particles in a one-dimensional situation where the interaction has a delta function as the kind of potential. And there's the Yang-Baxter equation. The next thing, of course, is connection is Donaldson's work. And here Peter already mentioned, of course, Donaldson's original breakthrough using gauge theory. And then he defined these polynomial invariants. This is the way they looked like in Donaldson's paper. There are a lot of things can be done a bit more simply now. There's always the important restriction on the 4 manifold that B plus has to be bigger than or equal to 3 in order to have a well-defined invariance. And there are a couple of other interesting features about the invariants. The invariants depend on orienting, if it's, let's say, simply connected, orienting H plus of the 4 manifold. And then there's a sign change if you have a diffeomorphism that doesn't preserve the orientation of H plus. It has to preserve the orientation of the manifold itself, full stop. But anyway, and these are, again, polynomial functions on the homology, as Peter mentioned. So that's another important character. So the Yang-Baxter equation actually figures into von Jones's work, where he defines the Jones polynomial. And in particular, Jones defined interesting representation or family of representations, one parameter family of representations of the braid group, which he discovered from his study of von Neumann algebras, 2-1 factors. So scary stuff, but get this very pretty representations from projectors in this algebra. And then he observed that if you take a particular weighted trace, if you take a braid, apply this representation to it, take the trace, which is part of the definition of the von Neumann algebra, then with an appropriate factor, you get an invariant of the knot. And of course, we know that's gone on to be very influential. And the next character Peter mentioned briefly is instanton Floor homology. So this is Floor's 88 paper where the work comes up. And one thing to notice, so he unfortunately passed away too early, and in one of his posthumous papers, which appears in the Floor Memorial volume, he defines the first kind of gauge-theoretic knot homology. This is its definition. It's essentially, if you have a knot in the homology sphere, then it's essentially the knot homology is the floor homology of the zero surgery with a particular SO3 bundle on it. But anyway, so Floor's already defining an interesting invariant of knots and an very interesting invariant of three manifolds, as we saw. And just to say a tiny bit more than Peter did, so the Floor homology is the Morse homology of the Chern-Simons function. Here's the Chern-Simons function, written out in all of its glory. And the interesting thing is that when you differentiate it, then there's a 2 that appears here. And then, well, that 2 cancels, but there's 3 factors here. So you get rid of the 3, you get this. And this is just the curvature of the connection. So the differential derivative of Chern-Simons in a particular direction is obtained from the curvature of the connection paired with the direction that you're moving in. So the gradient, downwards gradient flow, in a natural sense, is this equation, which turns out to be equivalent, as Peter mentioned, to the anti-self-dual Yang-Mills equations. And as the previous 2 talks kind of used, the critical set of Chern-Simons then is the flat connections, and mod gauge flat connections are representations of the fundamental group. So this thing drifts, that's the problem. The longer you hold the button, the more you have to tip it up. Anyway, okay. Yes, so the critical points of Chern-Simons are representations of the fundamental group. Great. And so another very influential paper around that time is Atiyah's paper, Topological Quantum Field Theory. And he defines what, the kind of now popular definition of what a TQFT is. In his telling, it's a functor from a cobordism category, so the objects in the category are d-dimensional manifolds, and the morphisms are d+1 dimensional cobordisms between them, and it's meant to be a functor. I mean, the important thing to take away, we'll talk about how that plays out a little bit more in Donaldson and Floor theory in a bit, but the important thing to take away, in some sense, the most important thing is that there's a composition law. So that composition of cobordisms gives rise to composition of maps. And he observes that there are a bunch of things that seem to satisfy a structure like this. Floor-Gromov theory, Jones-Witten theory, Casson theory, meaning the Casson invariant. And then he notes that Donaldson Floor theory should be an instance of this. You can kind of do that. You can construct a kind of a functor. So if you have a pair of 3 manifolds and a 4 manifold with a collection of homology classes, then there's a well-defined map sometimes. So it's not really a functor on a cobordism category, but what's really important is that whenever all 3, you have a pair of cobordisms and a composite, as long as all 3 things are well defined, then in fact there's a composition law. So that's already, that's great. Maybe you don't need to worry about the category aspect of it, but that composition law is a really important idea. The restrictions on the 3 manifold in the first pass on this restrictions on B+. And again, you shouldn't take the TQFT thing, as a proper definition. You should take it as an inspiration. And then of course, Donaldson, Uhlenbeck, Taubes, they were very important in this, and you got to glue those instantons. Okay. Although this probably won't come up again in the talk. Another important thing that happened in those early days was this, another instance of the interaction between the math and physics community is, there was the Jones polynomial, which at the time was only defined for knots in the 3-sphere. And it was an interesting question whether you could define the Jones polynomial, an analog of it, for knots in a general 3-manifold. Witten gave a physics interpretation as a path integral of the Jones polynomial. And that path integral made sense for an arbitrary 3-manifold with a little bit of extra data. In a little over a year, Reshetikhin and Turayev figured out how to make a rigorous definition of what Witten suggested, and it's still a very active kind of part of what's going on in some parts of mathematics to really connect these two pictures. This is purely combinatorial. This is, it's still physics. It depends on a path integral, but for example, you can try to do stationary phase approximations and see if stationary phase approximations you can make sense of mathematically, and then you can try and see if they relate in fact to what the Reshetikhin-Turayev invariants give you. That's related to the volume conjecture, etc. And anyway, it's a beautiful story, and in particular, it's the Chern-Simons function that appears again in that path integral. So anyway, so Peter mentioned that we extended in a bunch of papers the notion of the Donaldson invariance to invariance of a pair, 4-manifold, and a surface in the 4-manifold using connections that were singular along the, like, as he said, in codimension, they had a codimension 2 singularity. So here I've drawn, instead the picture 1 dimension down, I have a knot, and I imagine a connection that has non-trivial holonomy asymptotically around a little linking loop. And so, as Peter mentioned, we proved the structure theorem for the Donaldson invariance. Here is what it actually looks like. The Donaldson invariants were determined by finite number of cohomology classes, which are lists of W2, integer lists of W2. And again, this is for a 4-manifold of simple type, whatever that means. Peter gave the definition. And in particular, for classes of non-negative square, you had this adjunction inequality. So these basic classes, as Peter mentioned, you might think of as generalizations of the canonical class. If this was a complex curve and a complex surface, this would be an equality when K is the canonical class, or minus the canonical class. Anyway, okay, so there's this extension, and then, well, you should build another functor. So now the input is a 3-manifold and a link in it, and if you have a cobordism of such, so cobordism of pairs, a 4-manifold and a surface whose boundary are these two 3-manifolds and knots, then you get a map, and you can extend it. We're now it's kind of polynomial invariant in a little more complicated sense. These alphas are homology classes in the complement of the surface, and they can also be homology classes on the surface. Not so many even classes, but that's still more structure. And then there's work of various people, Ali Daemi in particular, that kind of clean up this in the complement of the surface a bit. But anyway, we've got this more interesting gadget. The input is still SU2 at the moment, or SO3, but then eventually you get this functor. Now, the knot homology that we want to, one of the things that we want to connect to, there was this braid at the beginning. And every time, all three strands are interesting, the really interesting thing is when they cross. So the next strand is from the Jones polynomials, of course, Havanov homology. And here are so Havanov homology, of course, as I think everybody knows, is a homology theory associated to knots. Interestingly, and it categorifies the Jones polynomial. This is Havanov's statement from Havanov's paper where he related it, at this moment to the Kaufman bracket. But that's equivalent, and it's a Poincare polynomial of his bigraded homology. And here are the homology groups of some, Havanov homology groups of some torus knots, the T2M family, so the unknot, the Hopflink, the trefoil, etc. So that's another character. It took some time to make it into a functor. So this is defined for knots and links, but it took a few years from its definition. I mean, Havanov believed, I think, that it was true already, but and as Havanov, Barnatan, and Jacobson. And one important thing which really already is baked into the definition, but is you can view it also post hoc as a consequence of functoriality, the fact that there's the unknot connects some, the unknot is the unknot, forces the Havanov homology to be, of the unknot to be a Hopf algebra. So there's maps in both directions, and the Hopf algebra is the cohomology ring of the two-sphere, as everybody knows, I think. But another big inspiration for some of the stuff that Peter and I have done is of course, the work of Peter Ajvath and Zoltan Szabo, the Heegard-Floer homology. And in particular, just like Floer did, they defined an invariant for three manifolds and then shortly after defined an invariant for knots. And as did Jake Rasmussen, there's this, he, like Donaldson, had a thesis that was accepted. It's been, very influential. One of the papers that was a big influence on Peter and I was this paper of Peter O. and Zoltan that showed that the Heegard-Floer homology of a double branch cover, the hat version of it, received a spectral sequence from Havanov homology. So this is the kind of first place where the representation theoretical, the kind of statistical mechanics story starts to connect with the gauge theory story. Important, so Havanov's story has many important generalizations. I'll just mention the Havanov-Rosansky story where they generalize, thinking of Havanov homology as SL2, generalize it to SLN. So in this paper, and here you see what the Havana homology is for the, as a function of n, again for the same family of torus knots. So one of the interesting features of Havana-Frozansky homology is this kind of torsion, which needs, you'd like to have a geometric explanation for. It's also controlled by a Hopf algebra. The Hopf algebra is the cohomology of, in this case, for SLN for CPN minus 1. So this also has a generalization, important generalization. In fact, this is sort of the simplest version of it for an unknot. In Havana-Frozansky, you get to label each component of your knot, or it'll be a little more general in a moment, with an integer between 0 and n, and then the cohomology of Grassmannian starts to appear when you do that generalization. So an important lesson for us from the Havana-Frozansky story is that, and Havana's SL3 story, is that it's important to not just think about knots. You need to think about also trivalent graphs, which are often called webs, embedded in their story in a three-manifold. In the three-sphere. In our story, they can be embedded in a three-manifold. That's kind of now the universe that they tell us one should work in, and we should replace surfaces by certain singular two complexes called foams. And the kind of singularity that a foam can have is that it can have this potato chip with a upper dam singularity, which is locally trivalent vertex times I, or it can have a more interesting kind of singularity where the potato chip has a dam on the top and the bottom. So there's a singular point, unique singular point where the neighborhood looks like the cone on the one skeleton of a tetrahedron. And in the Havana-Frozansky, et cetera, literature, one should think of, if you pick an n, one should think of actually these trivalent graphs to be oriented, and they should have edge labels so that keeping track of the orientations, that say if there are two incoming edges and one outgoing edge, then the sum of the edge labels should be equal to the exiting edge label. So Peter and I didn't quite take up the foam thing, web and foam thing. By the way, these things are called webs. Now, if you ever looked at a spider web, for real, spider webs always have four valent vertices, basically. Okay, but there's actually a mathematical explanation for why they're called webs. It turns out that NASA, in, I think it was 1985, had some experiments about what happens if you give spiders substances. It turns out, quite appropriately, that if you give them caffeine, they make lots of trivalent vertices. So maybe that's why. I don't know. But you can look at it online. They gave them other stuff, too. So if you're bored, that's what you can do. Anyway, Peter and I didn't take up that story of webs and foams yet, but we did think about what happens for higher rank gauge groups and try to define an instanton knot floor homology. And for in our telling it for each partial flag, so a little bit richer than at least the early generalizations of Havana-Frozansky. Instead of one integer to each component, we're allowed to assign a partial flag, which is really just, determined, just have a partition of n rather than into more than two numbers associated to each edge. And then there was an instanton floor homology group, and that using instantons that are singular in codimension 2. And now you have a bigger, fancier machine, which now can take an SUN and give you a functor. But then we did something that kind of conceptually I think was quite important for us, which is the idea that, one of, everybody's bane as a young algebraic topologist is base points. You always just want to write down the fundamental group and you want to forget about the base point, and you know that your algebraic topology teacher is going to whap you. So, it turns out that actually the story is much smoother if you add a base point. So you have to add a base point to your 3-manifold, not to your knot. You could do it to your knot, that's a different story, but you have to add a base point to your 3-manifold. And then there's a rather robustly defined theory. As long as your 3-manifold has a base point, it makes sense. But then you have to pay for that, because if you have a cobordism, you don't just have to have a cobordism between the 3-manifold and the knot, another 3-manifold and a knot, but you have to drag your base point through the 4-manifold. But then, then it really is almost a functor. There's no, your 3-manifold has to have a base point, so it has to be non-empty. And the cobordism have to be able to drag a base point across. Now you might have several components with base points, and maybe there can be several paths that join various base points, and there are no restrictions on B plus anymore. So that's makes the story simpler, and it's rather easier to work with. Not easy, but rather easier to work with. For the SU2 story, you can prove exact triangles, etc. So there's a little bit of mistaken history. The observation I want to make is that this theory gives you a nice kind of explanation for what the Havana-Frozansky homology for these torus knots is. If you look at the critical point set of the Chern-Simons function, remember there's a base point. So if there's a base point, then I'm only going to think about gauge transformations that are the identity at the base point, morally speaking. And so you can figure out what the representation variety is, and you find that it's CPN minus 1 for the unknot, T to 1. For the Hopf links, it's CPN minus 1 and a flag manifold, the flag of, say 2 orthogonal one-dimensional subspaces in CN. You notice that the rank of the homology here recovers the n squared. You get n from the CPN, and this guy is a CPN minus 2 bundle over CPN minus 1. The rank of its homology is n times n minus 1, so that gives you n squared. And more interestingly, for the trefoil, there are 2 components, and one of them is the unit tangent bundle, and that nicely explains the torsion, because the unit tangent bundle there's one non-trivial differential in the Gießen sequence, or which is from the top to the bottom, and it's multiplication by the Euler characteristic of CPN, which is n. So the Havanov-Rosansky computations are rather hard. So I was mistaken. These are due to Jake. Josh did the more general colored version, at least for the in many cases. But the nice thing is that the nice thing about this story is that the instanton story gives you a nice way of starting to think about what the answer might be for some of these more complicated theories. There's several beautiful papers by Josh. I should have mentioned the paper by Jake Rasmussen as well, and there's another nice paper by Lob and Zentner on this, just trying to understand the representation variety and what it's telling you and what it might tell you about the combinatorial theories. So the other, now taking a step back, still working in the context of unknots, Peter and I were able to prove, inspired by Ashvath and Szabo, we realized that there was a spectral sequence to the instanton floor homology of a link in the 3-sphere in this based setting. That's this I sharp for SU2. And because we already knew that the instanton floor homology detected the unknot, we could conclude that Havanov homology detected the unknot. So, the kind of drumbeat of thinking about webs and foams kind of kept going. There's some beautiful papers of Kwaflik and Rose where they give a different interpretation of, different construction of Havanov-Rosansky homology using webs and using foams in a more interesting way. Finally, we realized that let's think about, let's think more seriously about webs and foams. So we started to think about webs and foams, and for some interesting reason, which I forget, we decided, actually it's because it was easier. We thought, let's do SO3 gauge theory instead of SU2. That's usually not a big difference, but the distinction is actually the space of connections is essentially the same. The distinction between SU2 and SO3 gauge theory is really what the gauge group is, because locally they're maps either to SU2 or SO3, but not every map to SO3 lifts to SU2. So this theory is a kind of a finite quotient of some kind of corresponding SU2 theory, very closely related. But one thing that made this kind of simpler for us is that we could really think about these things instead of as singular connections. We just would think about them as orbifold connections. So in the SO3 story, the holonomy is the linking holonomy around the link is, we're just going to fix it to be an element of order 2 in SO3. They're all conjugate to this guy. Interestingly, not interestingly, obviously, the critical set for the unknot is just again, there's the base point in mind, so the critical set for the unknot is just all conjugates of this matrix, which is a copy of RP2 inside SO3. So, in this case, this story our setup is defined just with Z2 coefficients. The Hopf algebra that's kind of behind it is the Z2 homology of RP2, which looks kind of like the Z homology of CP2. So it in some sense, has a closer relation to Hovanov's SL3 homology. And why was this interesting? So, we want to study these representations of the fundamental group, from representations of the fundamental group, we get this J-sharp instanton homology. And one of the theorems we proved in that paper is that if you have a spatially bridgeless graph, so let me just go back to my pictures of these guys. So here are these trivalent graphs, which I'm thinking of in 3-space. You notice that abstractly, this graph is just two circles with a bar. But this embedding of it, if you can see, it's sort of two linked circles with a bar. This embedding, there's no two-sphere that hits this guy only in one edge. Whereas if I look at this one, there is a two-sphere which hits it in one edge. So although both of these, in the sense of graph theory, have a bridge, in graph theory, a graph has a bridge. If you remove an edge, if it becomes disconnected, as a three-dimensional gadget, this one is bridgeless, this one is not. Yeah, so, oops, too far, yes. Yeah, so we proved that if it was spatially bridgeless, so that's an application, by the way, of the sutured instanton floor homology story that Peter had mentioned in his talk. So in particular, if you have spatially bridgeless graph, then they're non-trivial representations of the fundamental group where the meridians map to this elements of order 2. So how do you get representations of the fundamental group into SO3? Well, the easiest way to do it is to look for abelian representations. And SO3 has an interesting, little bit more interesting abelian subgroup, Klein 4 group, Z2 times Z2. These representations have a nice meaning in terms of graph theory. They're what are called Tate colorings. So if I think, I'm insisting that the meridian of every edge goes to a non-trivial element. And so I can think of an abelian representation, therefore, as defining a 3 coloring of the graph. So I think of the 3 colors as corresponding to the 3 non-trivial elements of Z2 times Z2, and then I have to have that their product is 1. That means they must be different at every vertex. That's a Tate coloring. So the Tate colorings, here's a Tate coloring of the one skeleton of a dodecahedron. We'll look at the number of Tate colorings, so number of abelian representations of the fundamental group of the complement. There's 6 for this guy. This come from permuting one obvious permutation. There's 60 for this guy. There are 10 distinct up to permutation colorings of the dodecahedron. And this is the Peterson graph. The Peterson graph has as kind of in the graph theories, it's a quotient of the dodecahedron by a free action of Z2. It has no Tate colorings. It's smallest, in some sense, smallest non-planar graph, but it has beautiful, interesting embeddings in the three-sphere. What do we know about instanton homology versus Tate colorings? Well, one thing that we proved is that for graphs for planar graphs, the dimension of this J sharp was bigger than the number of Tate colorings. We conjecture that it's actually equal if the graph is planar. So that's interesting because we have this non-vanishing theorem, and if our conjecture is true, then that would be, which would be so nice these days, a computer-free, think about that, proof of the four-color theorem. Somebody do it, okay? I hope OpenAI is not listening to this. Anyway, that's one fantasy. And it's led to some quite interesting work. Our paper, in any case, there's beautiful work of Havanov and Robert, which we kind of had a story about how to evaluate foams in the gauge theory context, which we didn't know how to actually, we didn't have a formula for evaluating them. We said how you should be able to evaluate them, and they came up with a beautiful way of finding a formula. It was very much, it was closely related to the work of Robert and Wagner. Well, what have we been doing lately? So we decided to take a baby step. We went from SO3, we'll do SU3. Why not? Again, we're going to think about orbifolds. Actually, it turns out orbifolds are a very nice way of kind of making sense of why trivalent and why conon tetrahedron. The point being that, a bifold in our terminology is an orbifold where the local, if the group at a point is, if it's non-trivial, then it's either Z2 times Z2, that's in dimension 3, and in dimension 4 it can also be Z2 cubed. But then you notice that the quotient of R4 or R3 by these groups is actually homeomorphic to R3 or R4. And so if you have a web in a 3-manifold or a foam in a 4-manifold, then you can, in a rather canonical way, define an orbifold from that data and just think about doing orbifold gauge theory. Now, then we thought, okay, we'll do orbifold gauge theory, but instead of SU2, we'll do SO3, we'll do SU3. Now, the reason that we were interested in this is that, well, SO3 is the fixed point set of an involution on SU3. And you might hope to attack the conjecture, the conjecture about the lower bound, using some version of Smith theory. So if you just look full stop at, if you look at SU3 connections, mod gauge on a manifold, and SO3 connections mod gauge, you can think of the C3 bundle, you can do complex. If it admits complex conjugation globally, then, or in other words, it's the complexification of a real bundle, then you can, the SO3 quotient space is a subset of the SU3 guy, and it's the fixed point 7 involution. So you might hope that Smith theory would apply. Okay. Anyway, so we studied that, and what we were able, so we again get a nice functor from this pointed cobordism category. And what we were able to prove is that, in fact, if you have a planar graph, a planar web, rather, then, and we only did this over with Z2 coefficients, by the way, also for SU3, then, in fact, the rank of the Floer homology group that we defined is the number of Tate colorings. This uses, exploits some calculations that were done by Xia and other work of, work of these, of Xia, Daemi, and Scaduto in various combinations. However, unfortunately, again, the bane of everybody's algebraic topology life is the base points. The way we introduced the base point, in a sense, destroyed the conjugation symmetry. So this particular result doesn't help, but it's a little more motivation that maybe that conjecture is not nuts. Anyway, currently, what we're trying to do is do an analogous story for higher rank, for SUN in some generality, and also sorting out what's going on over the integers. But that's still, like it says here, under construction. And the machine isn't quite built. But we're hoping to do that. And so we aren't allowed to say the B word, right? So I'm not. But nonetheless, to end my talk, I want to thank these two guys for the great math that they've done and the years of friendship, and I hope both continue for many more years. And, well, okay, sorry, I finished early.
All right, are there any questions for Tom? Yes.
Question right over there.
Maybe this is a bit naive, but how does your result on webs sort of, or modulo the conjecture, imply the four-color theorem? If the webs you're doing are only like trivalent when four-color theorem is like all graphs?
It's an observation of Tate's that three-coloring. If you have a planar graph, then you can go back and forth between a three-coloring of the edges and a four-coloring of the complementary regions. And the idea is quite simple. You just imagine you have this planar graph, and you have these three, let's go from the three-coloring to the four-coloring. That's the interesting direction. Imagine your fourth color is white. So color the outside white. Every time you cross an edge, you're going to change the color. If you go from a white region across a red edge, then you color that region red. But now, okay, and et cetera. But now if you're in a, say, blue region, I forgot what three colors I used, and you cross a green edge, then you end up in a red region. And you check that that's consistent. That's a consistent way of defining a coloring, and that's why it's equivalent. And also, I mean, it's also easy to see that it's enough to do the trivalent, where the map only has trivalent edges between vertices between borders. So, yeah.
Other questions?
No, no. No, it can be white in the middle. There can be white in the middle. So similarly, if you're in a blue region and you cross a blue edge, it becomes white. Yeah. So there can be white patches. Yeah.
Other questions? Okay, then let's thank Tom again. And let's meet again in maybe 15 minutes, 11:55, for the next talk.
Should not start before the scheduled time.
All right. Maybe we should begin the next talk. Everybody, please. All right, so for the last talk of the morning/lunch session, we are pleased to have Aliakbar Daemi, who will tell us what we can learn from instantons if we don't think rationally.
Right. Thank you. It's a great pleasure to be at this conference, giving this talk in this beautiful hall. I want to start with a disclaimer and an apology. So the talk that I'm going to give is going to be based on 2 papers and 1 book. None of them has appeared yet, so you should take the result with some grain of salt. When I gave my title and abstract, it seemed likely that at least one of those papers would appear on archive. Hopefully, I think it's still think that it could appear sometime soon, so hopefully there will be something that you can go back in case you're interested for more details. Okay, I want to also start with, like the other talks in the morning, the long talks with some prehistorical fact about, this time about 3 manifolds. So if you have a closed-oriented 3 manifold, there's this theorem of Wallace and Licorice, which says that you can present this 3 manifold as a surgery on a frame link in S3. So that would motivate some measure of complexity on 3 manifolds. You can define surgery number of your 3 manifold, which is defined as the minimum number of connected components of such a link L. In dimension 3, we have a generalization of surgery. We can talk about dense surgery. So you can also use the notion of dense surgery to define another complexity. So now you start with a link. You start with a 3 manifold. You want to present that link as dense surgery on a link in S3. So now you have more flexibility. The components of your link are now rationally framed. And you ask, what is the minimum connected components of such a link? From the definition, because dense surgery is more flexible, it's clear that the dense surgery number is less than or equal to the surgery number. So if you want to start studying something about 3 manifolds, perhaps homology would be the first tool that you want to use. Whenever you have a 3 manifold which is dense surgery on an n-component link, immediately you know that its first homology has a generating set with n elements coming from the meridians of your link. So in particular, if your first homology is big in the sense that you need a lot of generators for the homology, then either of the 2 surgery numbers it has to be big. So as an example, if you look at T3, then it's surgery on Bromian ring with 3 components. So you know that surgery numbers for T3 are at most 3. On the other hand, homology, for homology you need at least 3 generators. So in this case, you can determine what surgery numbers are. There's a case that you cannot say anything based on homology, and that's the case of integer homology spheres. So in particular, it's natural to ask here if you can construct integer homology spheres where the surgery number of the three-manifold, or even better, the dense surgery number is arbitrarily large. So there's a more precise statement of this is due to Dave Oakley, which for some reason, which is not quite maybe necessary, but he asked for, in addition to being integer homology sphere, he asked about whether you can find irreducible toroidal integer homology spheres with large either surgery number or dense surgery number. The other question that he asked, which seems very reasonable, is that if you start with a bunch of non-trivial three-manifolds, not homeomorphic to S3, and if you take the connected sum of n such three-manifolds, then the dense surgery, you would expect that the dense surgery number of the connected sum would be of the order of the sum of the dense surgeries, particularly because these are non-trivial three-manifolds, each of them would contribute at least one, so you would expect the dense surgery number of the connected sum has to be n. And he asked whether this is always the case. So the theorem that I want to talk about is, the first theorem is in joint work with Xingpei Liu and Mike Miller-Eismeyer, which answers the first part of the question. Says that for any n, there is a hyperbolic homology sphere so that both of the surgery numbers are exactly equal to n. And we can say something related to the second part. It's by no means close to addressing the second part, but like, for instance, if your three manifolds that you're taking the connected sum of are from this list of, Wait, how am I supposed to go back? Oh, okay. Okay, good. So if you look at this list of Briscoe homology spheres, with this, and there's a typo here, this sigma KL, and here n has to be L. So you're taking Briscoe homology sphere with these three parameters. You take n such guys, they don't have to be the same thing, and you take the connected sum, then their surgery number has to be, in fact, it turns out it's exactly equal to n. Let me mention also some earlier results related to this. You can use a lot of different tools from three-manifold topology to study this problem. And it turns out that it's hard to go beyond showing that surgery number is greater than 2, but like to get to 2, there are a lot of different tools that you can use. For instance, Boyer and Linus use Casson invariant to construct homology lens spaces with dense surgery at least 2. Dave Oakley gave the first example of an integer homology sphere with dense surgery number at least 2, and he uses Yang-Mills gauge theory to do this. Using Higgar-Floor homology, Karakurt, and Ledman, they give examples of both Seifert-Fibered and hyperbolic homology spheres with dense surgery number at least 2. They satisfy also some other interesting constraints. You can also construct homology S1 times S2 using Higgar-Floor homology with dense surgery number at least 2. This is work of Head and Kim, Mark, Park. You can also use SU2 character varieties. So Sivek and Zentner use SU2 character varieties to study homology lens spaces with dense surgery number at least 2. There are works of Leo Piccirillo and then later on Azar Pendar who use Fruita's 10/8 theorem. And finally, I mean, you might expect, I mean, maybe the second thing that you want to do after homology is to use fundamental groups. And so if you have a link, if you have a three-manifold, which is surgery on an n-component link, you know that the fundamental group can be normally generated with n generators, again, coming from the meridians. But in general, it's hard to control the number of needed generators for fundamental groups of 3 manifolds. In fact, it wasn't until very recently that we didn't know if there is an integer homology sphere which its fundamental group has weight greater than 1, meaning that you need more than 2 generators for the fundamental group. So in particular, this work of Chen and Loda, it gives examples of homology spheres with dense surgery number at least 2. So the strategy of the proof, the key ingredient in the proof is an invariant due to Frobisher. It's called Q3. It's because there's a label 3 there, you might expect that there's a Q2 invariant, which is you're right, there is a Q2 invariant, but you might also expect that there's Q1, but there is no Q1, so there are Q2 and Q3. I'm gonna mention I'm gonna say a few words. I'm gonna review a quick definition of Q3 later in the talk. But let me, before doing that, let me just state some theorem which gives discusses some properties of this invariant. So in collaboration with Mike and Chris Scaruto, we studied connected sum with, maybe before doing that, let me emphasize on the point here, which is also related to the title of my talk. It's important here to work, for the results here, it's important to work with instanton homology with Z mod 2 coefficient. It's not out of laziness that you don't want to work with orientation. So it looks like an instanton homology with Z mod 2 coefficients behave very differently with instanton homology with rational coefficient. So in collaboration with Mike and Chris Scaruto, we studied how instanton homology behaves with respect to connected sums, instanton homology with Z mod 2 coefficients. In particular, something that one can show is that Q3, we don't quite know if Q3 is additive with respect to connected sum, but what we know is that if one of the summands is a spatial, for instance, something that we know, if it is one of the summands is Seifert-Fiber homology sphere, then it is additive. The other important ingredient for us is this inequality. So whenever 2 3-manifolds, 2 integer homology spheres, in fact, they don't have to be integer homology spheres. There's some version of this for rational homology sphere. It's easiest to state this in the generality of F2 homology sphere, which includes integer homology spheres, that if you have 2 integer homology spheres and some cobordism between them, you can still define Q3. And you can look at the difference between Q3 of the 2 ends. And what is true is that the difference between Q3s is bounded above and bounded below by this topological invariant of your cobordism, bounded above by B minus, and it's bounded below with minus of B plus. And the last part, this is, once you know the definition, this part 3 is just some simple observation, but it's useful to record it here. So one thing is that Q3 it behaves nicely with respect to change of orientation. So if you change the orientation, Q3 also changes orientation. So in particular, that implies that Q3 of S3 is 0. And you don't need that. You can, once you know the definition, it's almost obvious that like Q3 of S3 is 0. So the next 3 manifold that you might want to know what is its Q3 is the Poincare homology sphere. And it turns out that in that case, it's non-trivial. It's equal to 1. Any questions up to this? Yes? Sorry, can you repeat the first one? Why we're assuming that it's Seifert-Fiber homology sphere? Oh, yeah, sorry, yes. Yeah, this means y, well, first y is an integer homology sphere, and y prime has to be Seifert-Fiber homology sphere. Right. That's not true.
Y prime is anything.
Y could be anything. Y doesn't have to be Seifert.
No, but in item 2.
Oh, in item 2, yeah, y and y prime are arbitrary. Yeah, the assumption here is only for part 1. Yeah. For part 2, you can even assume that y and y prime are F2 homologous sphere. But for part 1, there are some connected sum theorems that we have for more generality, but at this point, they're not strong enough to get something about Q3. Okay, let me make some comments about this Q3 invariant. In fact, this Q3 invariant, it has some predecessors. The first one is Frobishev's H invariant, which is defined using instanton homology with rational coefficients. And I think the motivation to define, his motivation to define this invariant was to extend Donaldson's diagonalizability theorem to the case of manifolds with boundary. So in particular, if you have a cobordism, if you have a 4-manifold W with boundary Y, which we assume that it's negative definite, and it has a non-standard intersection form, then he showed that under this assumption, H invariant has to be greater than 0. So in combination with the computation for H invariant of S3, which is supposed to be equal to 0, you can see that you would get the extension of, this generalizes Donaldson's diagonalizability theorem. So here you also have some sort of inequality, but an important assumption, like Donaldson's theorem, is that B plus is equal to 0. So if you have a cobordism from Y to Y prime, with B plus is equal to 0, then you can say that the H invariant of the outgoing n is at least as big as the H invariant of the incoming n. And this invariant, it has cousins in other floor homological invariants. Like for instance, in Higard floor homology, there's a similarly behaved invariant, which is called correction term, defined by Oishwath and Zobos. And in monopole floor homology, also there's some invariant, which is also called H invariant. So this is defined by Frobishev. Some extensions of this invariant is introduced in a paper by Peter, Zoltan, the other Peter, and Tom, where they study lens space surgeries. I want to emphasize here that there is some key, so these are all, they satisfy similar inequalities, which the assumption is that B plus is equal to 0. Some key feature of Q3 here is that you don't need that assumption. So you can still get control. You can get some inequality between the difference of the Q3 of the ends, even when your cobordism is not negative definite. And this is the point. I mean, you still need this assumption. Maybe I didn't think it was in my slide, but maybe I didn't say it out loud, that you still need some assumption on H1. You want the first homology of your 3-manifold to be, you don't want any two torsion in that first homology. But under this assumption on first homology, you would get an inequality like this. Yeah, I think this is probably a good place to make a comment about my frustration with Higard floor homology when I was a graduate student. Since this is neither Zoltan's nor Peter's birthday conference, I think it's probably okay. So when I was a graduate student, I worked in defining some knot invariant using Yagman's gauge theory with higher rank bundles. And when I would go to talk to Zoltan's and Peter's students, and they told me that, yeah, in my lunch break, I computed the invariant of this 11 crossing knot, and proved this cool thing about the non-orientable genus of this knot. And then they would ask me, what did you do? I say, I'm working on this knot invariant, and I don't know how to compute it for the unknot. But as I grew up, at least mathematically, I started to appreciate Higard floor homology more. I think it was influential in most of my work. It always gave some good guide what to do with my research, even though I usually don't work directly with Hilgard-Floer homology. And the other thing was that to look for some, it looked like it, instanton homology, which most of my research is about it. It looks like it's very similar to Hilgard-Floer homology, but then there are places that they diverge from each other. Like sometimes you can take, one thing that you can take advantage of it is in instanton homology, there is this Chern-Simons filtration. And it looks like it, working with Z-mod 2 coefficients, the two theories also diverge from each other. Doesn't look like they behave similar to each other. All right, and of that, let's get to say something about proof of that theorem. Actually, the next thing that I want to talk about is how to use these properties of Q3 to say something about the dense surgery result. So let's say that you have a 3-manifold, which is surgery on an n-component link, like Y. Then that link would give you a natural trace cobordism, a 2-handle cobordism from S3 to Y, with B2 being N, and first homology being trivial, so in particle B plus and B minus are 0. So from this, you can, in the inequality in the second part of the theorem, you can see, this is the first part of the inequality, you can see that the minus Q3 of your 3-manifold Y, which is given by surgery on n-connected component, is less than or equal to B plus of W minus Q3 of S3, which is 0, and this is less than or equal to N. By changing orientation, you would get, in fact, the absolute value of Q3 is less than or equal to the surgery number. So that's for the case that you're looking at integral surgery. But there is some standard trick that you can use to go to the case of rational homology sphere. So if you have a rationally framed link, you can use a bunch of slam dunk moves and adding a chain of unknots to your link so that you would get a link an integral surgery presentation for your 3-manifold. So the recipe is that the coefficients are given by, I don't know why this pointer doesn't work. So the coefficients are given by this continued fraction R. So we can assume that all the AIs except the first one are at least -2. And that would, when you look at the cobordism associated to this integrally framed link, you can see that it is still true that B plus is at most N. Now you increase B minus, but B plus is at most N. So you would get a similar inequality for dense surgery number. Okay, so that means that if you can construct examples with large Q3, then you can get 3 manifolds with large surgery numbers. So let's look at first connected sums of Poincare homology sphere. So let's say P is sigma 235. It's Poincare homology sphere. There's a typo here. This P is supposed to be 5. And using the connected sum part of this theorem, so part 1, and the computation for Poincare homology sphere, you can say that for connected sum of n copies of Poincare homology sphere, you would get n. Another thing that you can see is that if you have a homology cobordism, then B2 and B plus are both 0. So again, the inequality can be used to say that Q3 of the n's are equal to 0. In fact, you can work with F2 homology cobordism. So what you can do is that now you can take a 3-manifold, which is homology cobordant, to the connected sum of n Poincare homology sphere. And what you would know is that the dense surgery number of this guy, by the inequality from the previous slide, is at least as big as Q3. And by homology cobordance invariance of Q3, it's equal to Q3 of the connected sum of n copies of P, which is equal to n. So in particular, we can take Y to be hyperbolic using some result of Myers. So this way we can construct examples of hyperbolic 3-manifold with a dense surgery number at least n. But this part can be also more explicitly. So there is this example of families of examples of hyperbolic manifolds, which you can construct. So if you take this knot, which was handed to us by Hayden, so like if you just take, here we have 3 trefoil, and they're connected to each other by some bands. So if in general, if you have n left-handed trefoil like in the picture, and maybe you add some twists here, and do -1 surgery on this 3 manifold, you would get a hyperbolic, -1 surgery on this link, you would get a hyperbolic 3 manifold. And because this link here is concordant to the disjoint union of n trefoil, you can see that the resulting 3 manifold is homology cobordant to connected sum of n Poincare homology sphere. Any questions? Okay, let's do some more computations. So this is related to the second part of the theorem. So like, remember there was this family of Briscoe homology sphere. Now there is no typo. These are all L, except that there is another typo here. This n has to be L. So this sigma KL is supposed to be -1/L surgery on the left-handed. I mean, this Briscoe homology sphere is -1/L surgery on the left-handed two-bridge not T2 2K -1. So in particular, because it has surgery presentation with one, on a surgery presentation in terms of a knot, you see that the absolute value of Q3 has to be at least 1. You can see that also there is a negative definite cobordism from Poincare homology sphere to this guy. It's not hard to construct such a negative definite cobordism. There's a standard negative definite cobordism from -1 surgery on the left-handed trefoil to -1 surgery on this guy, just because by some crossing changes, this guy is related to this. Of the same sign, crossing changes of the same sign. And then you can get a standard negative definite cobordism from -1 surgery to -1/L surgery. So in particular, what you can say is that Q3 of all of these guys is at least 1. We already knew that it's at most 1, so they are all equal to 1. So now using the connected sum theorem part of the theorem, you would see that Q3 of the connected sum of n such 3 manifolds is also equal to n, and you can use that to get some lower bound on the dense surgery number. I want to spend just very briefly on making some comments about another direction that you can use these properties of Q3 to say something about knots and 3 manifolds. This is based on ongoing joint work with Duncan McCoy and Mike Miller-Eismeyer. So let me just go back to the inequality. So the inequality for Q3 was that, let's say in the special case that you have a 4 manifold with 1 boundary, you can regard it as a cobordism from S3 to Y, and you would get this inequality. You can make this inequality a little bit weaker. Just say that like the absolute value of Q3 is at most equal to B2 of your cobordism. So now, let's assume that your cobordism W, or your 4 manifold W with boundary Y, is coming from a branch double picture. So everything comes from a branch double description. So Y is branch double cover of a knot in S3. And you have an embedded surface bounding your knot in S3 with even homology class inside some 4 manifold X, which with trivial H1. And your W is the branch double cover of this embedded surface. So the inequality here would imply that the Q3 of the branch double cover, its absolute value, gives a lower bound on the B2 of the cobordism, the 4 manifold upstairs W, which you can see that it's equal to twice the B2 of X plus twice the genus of S. So you can think about, you can now fix X and try to see what you can say about such an embedded surface. So you have you're looking for an embedded surface bounding your knot inside a fixed form manifold X. So this kind of slice genus got attention recently, various reasons. But something that you can see here from this inequality is that if you fix X, you fix your knot. If you fix X and assume that your knot is chosen so that like this guy is large, then you would get some lower bound on the genus of your surface. So in particular, you can conclude that if you have, for some X with this constraint on this first homology, there is a knot which is not a slice inside X if you assume that the homology class of the slicing disk is even. In order to be able to pass to the branch double cover, you need that assumption. Let me make a remark that there are classical results of Norman and Suzuki. They independently show that any knot is a slice, for instance, inside S2 times S2 and connected sum of CP2 and CP2 bar. So we're not making any contradiction with this because we are assuming that the homology class is even. And I think in the light of this theorem, it's natural to ask if this can be done also with respect to other primes. Is it possible to show that there are disks, there are knots in some arbitrary form manifold so that it is not slice in your form manifold if the homology class of the slicing disk is divisible by P, if that's part of the assumption. And I mean, this is, by no means, this is like supposed to be some strategy, but like one might try to do SUP instanton homology with this structure group with coefficients in FP. And the problem is that even defining this instanton homology is not obvious. You might, if you start thinking about these things, you might have the same existential problems as the ones that I had as a graduate student. Maybe just because I'm going slow, let me just quickly just say one thing that like one other application and and then move to to the proof of this theorem. So using similar line of idea, you can also say that like there is for any smooth closed form manifold X with trivial H1 with Z-mod 2 coefficients, there is a knot such that this knot is topologically H slice, but not a smoothly H slice. And H slice here means being a slice, but with trivial homology, so that the slicing disk is supposed to be, which it should have trivial homology class. And this, I mean, there was a question asked by Cyprian, Marco, and Lisa, whether this is always true for any X. So no constraint on the first homology, and at least in the case that the first homology is 0, we can use Q3 and its properties to produce such examples. Are there any questions? I want to switch gears and talk about what would go into the proofs. Maybe here just I want to give some credit here. So like this was so like this direction to explore like whether Q3 can be used to say anything interesting about this slicing problem was inspired by a talk that I think Andras gave about a year ago, and we had some follow-up discussions. It was a beautiful talk, very helpful discussion afterward. Again, it's too bad it's not his birthday conference. But yeah, thanks for that. All right, so I want to talk about what would go into the proofs. That would require talking a little bit about equivariant aspects of instanton homology. So I want to even do something more elementary, just equivariant homology for topological spaces. So let's say that you have a Lie group G. And I'm going to assume that this Lie group G has a CW complex structure. And the multiplication map is cellular with respect to the induced cellular structure and the product, and the fixed cellular structure and G. So for instance, these are some examples. On S1, you can get such a CW complex structure when identity is the 0 cell and everything else is the 1 cell. For SU2, identity is the 0 cell and everything else is 3 cell. The one which is more relevant for this talk is SO3. SO3 topologically is RP3. So in particular, it has a CW complex structure with 1 cell in any dimension between 0 and 3. And you can make, it's not hard to see that you can make it compatible with the algebraic structure. So there is a cell structure like this. So something that you would get out of the cell structure and the multiplication is that this guy, I mean, you can look at the cellular chain complex of your Lie group. So it's a chain complex. But using the multiplication map, you would also get a multiplication map on this cellular complex. In particular, you would get, there's a typo here, it's a DG algebra structure and this chain group. So in the special case of S1, this DG algebra is the exterior algebra in one generator in degree 1. For another typo, this is supposed to be SU2. For SU2, this is again exterior algebra in one generator, but oops. That generator is in degree 3. And for SO3, you would get something more interesting. Now you would get the exterior algebra in 2 generators. By the way, I'm working with F2 coefficients. So that's one place that like F2 and rational would behave differently, because eventually we want to do some SO3 equivariant instanton homology, and with F2 you have this description with rational coefficient. That's not the case anymore. So now if you have a topological space with a CW complex structure and with an action of G, so like because it has a G action, you have this multiplication map, the action map. And if you assume that this is cellular, then we would get a DG module structure. I mean, just the associated map to this, the chain map to this guy would give us a DG module structure on X. It's a DG module over this DG algebra of your Lie group. So in particular, this would give you a framework for doing equivariant homology for spaces using, if you want, the chain model given by CW, by the cellular chain model. It's not, I put equivariant in quotation mark because this is not equivariant homology of your space. But what is true is that there is some algebraic operation called causal duality that you can apply to this guy, and you would get some explicit chain model for the equivariant homology of your space X. Because we want to eventually do floor theory, we would like to adapt this construction to the case of floor theory. So we want to work with X, which is now a manifold, and we have a function on this manifold, smooth manifold, and we want it to be G invariant Morse function, which means that it's Morse spot, but the critical orbits, the connected components of the critical set are all orbits of the G action. You need some additional assumption, but what you can do out of this is that you can still construct a DG module structure over this DG algebra, now coming from critical orbits and Morse trajectories of F. So to be a little bit more explicit, this F here, this chain group is generated by cellular complexes of the orbits with some differential D here. So this D has two kinds of contributions. So it has some internal differential coming from the cellular differential here and some external differential which is defined in terms of Morse trajectories. I don't think this is original or anything, but like one place that this is hopefully going to be discussed is this book that I'm working on with Mike and Chris. All right, so now we want to go back to 3 manifolds. So let's say that you have a 3 manifold with some, we want to do some gauge theory. So there's going to be, you're going to see some words which already appeared in Tom and Peter's talk. So you want to do gauge theory in this 3 manifolds. So like you need a gauge group. The gauge group that we want to work is, you start with a trivial SU2 bundle, and the gauge group is the space of all maps from your 3 manifold into SU2. For a reason that becomes clear in a second, I'm going to assume that at the base point, this gauge transformations are equal to 1. I want to look at the space of all connections on this bundle, but I want to, if 2 connections are related to each other by pullback with respect to the action of this G0, I want to regard them as the same. So I'm taking the quotient with respect to this gauge group. So this is not the usual configuration because we modeled by the whole transformations here. I'm assuming that the transformations at the base point is equal to 1. So this is the framed configuration space of framed connections, if you like. The reason that I'm not taking quotient by everything is that this guy is now some smooth, infinite dimensional, but a smooth manifold. Whereas if I took the quotient by all automorphisms of the bundle, I would get some connections with non-trivial stabilizer. So the quotient wouldn't be smooth. But nevertheless, we can take action of arbitrary automorphisms. So like we can just, without any constraint on what is the value at the base point. And these actions are trivial if the value at the base point is plus or minus identity inside SU2. So this way you would get an action of SU2 mod plus or minus 1 on this configuration space. So SU2 mod plus or minus 1 is SO3, so this way you would get a space with SO3 action. There's a Chern-Simons function that you can define in dimension 3. So, and you can still do it here. And just because the way that I set up this theory, and I'm working with frame connections, this is going to be some SO3 equivariant functional on the space of connections. So we want to do something similar to what we did in the case of in the finite dimensional case. We want to look at the critical points of the Chern-Simons functional and the orbits there and use that to construct the chain complex. So let's assume for simplicity Y is an integer homology sphere. This can be done more generally for rational homology sphere. So like in the case that this integer homology sphere, the critical points, in general, critical points of Chern-Simons functional, they all come from flat connections, orbits of flat connections. So in this case, because it's integer homology sphere, any flat connection is either irreducible or the trivial connection. So you would get some orbits of irreducible connection would contribute the homology or the chain of SO3. So this is what you would get, and the trivial connections would contribute just one sum n. So more explicitly, so like the irreducible chains on Y, you have they appear, each irreducible connections contribute 4 sum n's, and irreducible one contribute 1 sum n. And this is a module over this DG algebra of SO3. In the obvious way, the DG modular structure is defined. And there's a differential. So the differential, I mean, just because the differential has to be SO3 equivariant, it has to be a DG module homomorphism. So it has to commute with the action of chi1 and chi2. You can see it's an easy exercise to see that it has to be basically have this form. A lot of sum n's a lot of entries in detail. When I'm using the matrix form with respect to this splitting, a lot of terms, they have to be 0 because this detail has to commute with chi1 and chi2. It's a differential also. This is what I want to call an instanton SO3 complex associated to Y. So let's unravel this a little bit, see what we get there. So like, remember this detail has to be a differential. So in particular, the first thing that you would see is that d1 squared is equal to 0. So the terms which appear in most of the diagonal terms. And you can take the homology, and this is going to be the first version of instanton homology which was defined by Floor with Z mod 2 coefficients. You can do it with any coefficient ring that you want. Here we're working with Z mod 2 coefficients. I'm going to call this irreducible instanton homology. Associated to this D2 and D3, again, the differential relation would imply that D2 and D3 are both equal to 0. And this way you would get two operators, U2 and U3, acting on homology, instanton homology of Y. Associated to delta 1 and delta 4, you would get some functional. They satisfy this relation, so in particular, delta 1 would give you a functional, F2 valued functional, and delta 4 would give you an element of I of Y. So again, there's a typo here. This is supposed to be instanton homology of Y. And finally, the relation involving D4 would say that these two operators, U2 and U3, they almost commute. They don't quite commute. The failure to do so is given by these terms which are coming from flat connections. So this kind of instanton homology with Z mod 2 coefficients and with these operators and so on, with a slightly different chain model. This appeared in a very recent work of Roshoff, I think from either a year ago, 2 years ago. And in particular, even though this is not exactly in his paper, but this is you can define, so in his paper he defines the invariant Q2, but because for me it's more relevant to talk about Q3, I'm not going to define Q2, I'm going to focus on Q3. But this is also something that he's been giving talks about it for a while, so like this is something that, this is his definition. So Q3 of your integer homology sphere is defined in terms of instanton homology with Z mod 2 coefficient and these operators. There's a more conceptual way to think about this and to give this definition better than the definition here. So here the definition is just saying that when is your invariant is greater than or equal to I, it should satisfy a bunch of relations which they don't seem, I don't know, they seem to me at this kind of arbitrary, but they have some more conceptual meaning, which unfortunately I don't have time to talk more about this. But let's just, I don't know, stare at the definition for a second and just move on. So like the point is that there's a very explicit definition in terms of these operators. I mean, I guess at this point, the exact definition doesn't matter so much. And this is, again, I just copied the definition here. I want to make just maybe one small observation here. So the first point here is that this U2 and U3 are nilpotent. I mean, this is an observation, again, due to Roshoff. And you should think about this as the analog of this, the F2 analog of simple type condition, which came up in Peter's talk. So this U2 and U3 I mean, being not nilpotent is the, I don't know, I would think about it as the F2 analog of being simple type. Not that simple type, I'm not stating any conjecture that like, there's some Z mod 2 version of simple type here, but like this guy has a similar flavor as the simple type condition adapted to the case of three manifolds. So just because these operators are nilpotent, so in particular you can ask, what is the nilpotency order of this U3? As you can ask for two of them, but because we're more interested in Q3, I'm going to ask it only about U3. And that's something that, okay, we can just define a numerical invariant N3 of Y. So one observation that I want to make here is that if Q3 is less than this nilpotency order and greater than negative del nilpotency order. So for instance, from this property, it's easy to see that it's greater than or equal to nilpotency order. So if you just raise U3 to a large power, it becomes 0. So in composed with delta of 4, it would be 0 again. So it would be in the image of the U2 map, because this is just 0. This is something that I'm going to come back to it at the end of my talk. But okay, let me move on. One thing that I want to do in the rest of the 10 minutes remaining part of my talk is that give some ideas about the proof of this main inequality. What I'm going to do is that there's a more conceptual proof, which works in full generality, and then there's a simpler proof, which I think is not as conceptual, but I'm going to give it, first talk about the more conceptual proof. It's just the idea of the proof, and then give some more details for the simpler proof, for a weaker version of this inequality, which is still sufficient for the topological applications that I talk about. So the first thing is some simple observation that this is just really, here we have really one inequality. I mean, the other inequality can be obtained from the first inequality by just flipping your cobordism and changing the role of incoming and the outgoing end to your cobordism. So I'm going to focus on this inequality. Like I said, Froshov's H invariant, which was the counterpart for Q3 with rational coefficient, this is, it satisfies similar inequalities, but for negative definite cobordism. So the point is that when you look at, similar to Donaldson's diagonalizability theorem, what happens is that the inequality with respect to negative definite cobordism for Froshov's H invariant, they come from interaction with the moduli space of instantons and abelian instantons. So these are the cones from Peter's talk, the candles at the end of the talk. So we, in general, if you work with some definite cobordism, what happens is that those reducibles, they can be perturbed away. So you cannot do, they are not there to give you similar contribution as in the case of negative definite cobordism, except one connection. In the case that you're working with negative definite cobordism, you can perturb everything except the trivial connection. And you might still hope that, okay, this trivial connection, you can get something, and that's actually turned out to be the key reason behind this inequality here. Point is that this trivial connection is obstructed in the sense that this is not cut out transversely. So you need to develop some algebraic model for how morphisms of these SO3 complexes take into account the obstructed gluing theory related to understanding neighborhood of these connections. And this is, in my earlier work with Mike Miller and showing that equivariant instanton homology for rational homogeneous sphere is well defined. We had to develop this in one way. There's some variation of this that we did in my work with Chris Scaruto in some singular setup, which is closer to what we do. The second one is closer to what we do for the proof of this theorem. There is also you don't want to deal with the bubbling issue. So what you do is that you divide your cobordism to smaller parts, each of them with B plus at most 1, and then you prove similar inequalities for each piece, and you put them together to get an inequality for the whole thing. One comment that I want to make here is that there's a similar issue in the original definition of Donaldson invariance. If you paid attention closely to one of Tom's slides, I think, either Tom's or Peter's slide. In Donaldson's original paper, he defined Donaldson invariance with some constraint on the degree of your Donaldson polynomial. The issue comes from something similar. There's a trivial connection which would mess up with the definition of Donaldson invariance. Later on, John Morgan and Tom Mrowka, they use some trick which uses Boa formula to get rid of that constraint and define Donaldson invariant in all degrees. But if you go back to the trick, you would see that that's a trick which works with rings that because with rings that 2 is invertible. There's a 1/2 in one of the formulas which would show up. And that doesn't work with F2 coefficients. And somehow if you want to do this with F2 coefficients, Donaldson invariance with Z-mod 2 coefficients, they're not supposed to be very interesting, so maybe it doesn't matter there. But there is this issue that if you want to work with F2 coefficients, which you can use it to your advantage and get some more information from the trivial connection. I want to say a few words about the simpler proof of a weaker inequality. So I'm going to assume that my cobordism, I'm going to make this simplifying assumption that the incoming n is S3. It goes to Y, and I assume that my cobordism is a 2-handle cobordism. So in this case, we want to show that Q3 is at least negative of B plus. The next thing that I want to do is that I want to decompose my cobordism into simpler pieces. So it's, again, some elementary exercise to show the following, that after blowing up your cobordism W, you can write it as a composition of a bunch of smaller cobordisms, so that the last one, let's say, is a negative definite cobordism, so B plus is 0, and all the other ones are trace cobordisms of a knot inside an integer homology sphere. You're gluing a 2-handle to an integer homology sphere. So this is the splitting. So the last part is kind of similar to other Froeshov type invariants, like with rational coefficients, because it's negative definite cobordism. You can use a similar proof to show that Q3 of the outgoing end is at least as big as Q3 of the other end of the last piece. And recall somewhere I said something about nilpotency order of this U3, and there was this inequality, or half of this, or somewhere, I guess I mentioned this inequality, but here I'm looking at only half of it, that Q3 is at least negative of the nilpotency order of Y. So the claim here is that, again, so we have an integer homology sphere, and we have another 3-manifold which is given by -1 surgery on that knot. Then what is true is that the nilpotency order of Y and Y prime, they differ by at most 1. So this is there's an obvious cobordism from -1 surgery looking at the other way around, from -1 surgery to Y, which is going to be the kind of cobordisms that we get for W1, W2, all the way up to Wn. So in this case, there is this inequality between the nilpotency orders. So now what you can do is that, okay, you can use this inequality to say that the nilpotency order of Zi is at most the nilpotency order of the previous one plus 1. And you just go all the way back to S3 where the nilpotency order is 0. So this way you can show that nilpotency order of this nth one is at most n. And combining with this inequality, you would see that Q3 of Zn is at least -n. And by combining with this other inequality, you would get Q3 of the outgoing n is at least -n. Okay, so the key point are, in this sequence of inequalities, there are three facts that we use here. This relation, how N3 changes the nilpotency order with respect to these anocobordisms, and then there are these two guys. So by combining, let me maybe end by saying a few words. I have 20 seconds, maybe in the remaining 20 seconds I say something about the proof of this claim. This goes back to Freud and uses floor surgery exact triangle in the proof that he showed that U2 and U3 are nilpotent. There is a surgery exact triangle, which two of the terms are instanton homology of y and y prime, and that there's a third term where this is a sort of instanton homology that you don't have any reducible in your theory, so it's easier to work with. And this exact triangle is compatible with the action of U2 and U3. So the observation that is due to Freud is that U3 for these guys are trivial, for this so-called admissible pairs. And the reason is that secretly these theories are not SO3 theories. They can be lifted into some U2 theories. It's because these are coming from some U2, there's a U2 action going on there, and then you look at the associated SO3, you can see that the action of U3 is 0. It's the same fact that like if you have an SO3 bundle, and if you lift it into a U2 bundle, you know that the third H-Whitney class is 0. That's the obstruction. So here you would see that U3 is trivial, and just because this is exact triangle, you can check that that would imply that the nilpotency order for these two guys, they differ by at most 1. I was just going to say one quick comment about the connected sum, but I'm running out of time, so I'm just going to stop here.
Are there any questions? No.
So if there's two torsion, you might hope that your inequality holds, but just that you have to use the twisted B pluses of the, for each two torsion element, there's a double cover, and then there's a twisted B plus for that guy, which is...
You're talking about the assumption about H1 of
that's
W?
Right. Yeah.
So you want to use, I see. So you're saying that there should be some version of inequality that like the inequalities in terms of twisted B2 plus for the incoming and the outgoing end. Is that a fact or is that a question?
It's your theorem, I'm asking you.
Okay. I mean, the reason that we need this assumption, this is similar to this point which would go into proof of Donaldson's theorem B and C, that like he needs also some kind of similar assumption, and that has to do with having the number of central reducibles, reducibles on your 4 manifold. And because you're working with Z mod 2 coefficients, you don't want to have an even number of such reducibles. And that's why we need such an assumption. And you're suggesting that if we work with some... Yeah, I don't know right now how to use that. Yeah, I'm not sure if you would get at least with the same proof, the same inequality with twisted coefficient.
Other questions?
Hi, I was wondering if you were able to get rid of that extra Seifert fibered assumption on the additivity of Q3, and if you think that's true, I guess also like what are some of the technical obstructions to like getting a full additivity formula?
You're asking about additivity, right? Yeah. And getting rid of the Seifert fibered homogeneous sphere assumption? Yeah, that's a great question, partly because it's a great question, but also I can go back to my last slide that I didn't get to talk about. So in that case, what happens, we have some, for arbitrary integer homology spheres, we have some connected sum theorem for these instanton SO3 complexes. Oops. There is one subtlety here. One subtlety here is that the tensor product is not the naive tensor product. In some sense, you have to drive it. There are some additional terms. You have to add some higher order terms to the naive tensor product. And the conceptual reason behind this is that if you look at the diagonal map in SO3, and we talk about the multiplication map, and multiplication map is cellular, but the diagonal map is not cellular, and you have to homotopy it, but no, you have the product of homotopies, and you have to do some other homotopies, and if you keep doing that, you would get some sort of A infinity type relation. So these additional terms here, the perturbations are coming from that kind of contribution, which would complicate. So next to, but like in any case, you have a connected sum theorem. It's not the naive one, but still there is something that you can try to use it to study the behavior of Q3 with respect to connected sum. The reason that we don't have additivity of Q3 for all pairs, it's twofold. One reason is this, that there are these higher order terms. The other reason is that even if the naive tensor product would hold, you wouldn't still get additivity of Q3. There is something about Q3, the definition, which doesn't let you. There are some, when you try to apply that, there are some contributions from operators U2 in a way that it shouldn't be and messes up with that. That being said, we don't have a counterexample. It could very well be true that it is true for all pairs of y and y prime. In fact, I mentioned the version which was necessary for this talk, but there's a version of this additivity. So that if y is an integer homology sphere and y prime, so arbitrary, but y prime is surgery only, integer homology sphere surgery only on one knot in S3, then it would be still true. It would be still additive. So, just because there are these two different families, you might hope that maybe it works in some more generality, possibly for all integer homogeneous spheres. We don't have a counterexample for that.
Another question?
In Freushoff's work, which I don't know very well, there's a U2 and a U3, and as you said, he focuses on U2, and you focused on U3. Q2 doesn't have the properties that you would need to prove this theorem. It is additive, if I remember. I just wonder whether in the algebra, which is kind of a little complicated looking on the slide, is there a brief reason why it's U3 you need for this? And what's the difference?
So that why for U3 you would get that type of inequality for...
Yeah, there's some magic about Q3.
Some magic about Q3, yeah. I think there are two reasons, which it would be interesting to see how they are connected to each other. One magic is this observation here. Like I said, there are two different proofs here, right? So the magic in this observation due to Freushoff is that there is the base point vibration on the configuration space of ordinary configuration space of connections here, and that can be lifted into a U2 bundle. It's the same sort of argument that we will show that on the moduli of space of stable bundles, there's a universal bundle. So there's the base point vibration, in fact, for admissible pairs, it lives into a U2 bundle, which would imply that W3 of the base point vibration is trivial. And that's how it affects it says that the difference between the nilpotency orders of y and y prime are at most 1. What happens for Q2 is that it's not true, so this is not 0 anymore for the U2, action of U2 on this one is not 0, but it would be still nilpotent. And that's, again, this is an observation due to Frobisher, and from this he can show that like nilpotency orders of these two guys, they differ by something which is bounded by, I mean, or you can bound it, I'm not sure if is stated in this generality, but like something which is true is that you can control the difference between nilpotency order of U2s by the genus of your node K. I mean, not living in Y. So that's the magic behind the argument, the second argument. For the first argument, so what happens is that Q3 is related to W3. That's why it's called Q3. And when you work with the trivial connection, whenever it's obstructed, when you do gluing theory, you want to understand the neighborhood, so you have to work with some base point vibration. So the sections of base point vibration would be relevant. And in this case, the base point vibration is a rank 3 bundle, so W3 of that bundle shows up when you are trying to understand obstructed gluing theory. So that's, I think, the reason why the first argument would work to give you this kind of inequality using the first argument. There's a question in front.
Can you comment on some more conceptual ways of thinking about the QIs and the UIs?
Q1 is not defined?
Q2, Q3, and U2, U3.
Sorry, I didn't quite
Can you comment on some more conceptual ways of thinking?
Oh, the conceptual way of thinking about that. Yeah. That's a good question. Let me see if I can use the slides to do that. Let's go back. I mean, okay. It goes back really to the case of S1 action. Just one, this is slide. So when you look at the case of S1, the algebra it's generated by one element. It's the exterior algebra in one element. So you would like, okay, you try to understand DG modules over this algebra, at least the kind of DG modules that you would get from, let's say, let's say, Seiberg-Witten theory, where it's an S1 equivariant theory. There's one reducible, let's say you fix also a spin C structure, or you work with an integer homology sphere. There's one reducible, and then there are a bunch of irreducible generators. You would like to classify such DG algebras, DG modules, with respect to the kind of morphisms that you would get from homology cobordisms, which again, this kind of cobordisms, they induce a DG module homomorphism in a way that the reducible goes to the there's one reducible also on the cobordism. When you try to classify all such, you define something, where you look at all such complexes and you regard two things equivalent to each other if there are maps like this between them, then it's easy to classify all such things. And there is only one invariant, which is Frobisher's, basically it's a Frobisher's rational coefficient invariant. What happens when you work with SO3 is that now you have this bigger module, but what you can do is that you can forget chi1 or chi2. If you forget chi1, you would still get some modular structure over some ring, which is the same as the DG algebra of S1. So you cannot just use the same definition as there either. This is going to be like very similar to the definition of, if you're coming from a Higard floor size, the similar definition as coaxial term. But like also there is an instanton counterpart for that, which is the rational coefficient version of instanton homology. And that's what you would get, that's what Q3 is. If you forget the action of chi2 and only remember chi1, you would get Q2. You just have to shift this degrees by 1, and you remember the action of the right one, and that's QI.
Maybe we should just thank Ali again.
Thank you.
right, so a couple of announcements. The poster session will be at 2:30 at the Renyi Institute. So please join us for the poster session. I have been instructed to say that there will be coffee and pastries. So please join at the poster session. It will be from 2:30 to 4 at the Renyi Institute. And then after the poster session, we will meet back here at 4:30 for the clay lecture. And then after the clay lecture, we will have the banquet, which will be for everybody on the first floor of this building. So please come back here for the clay lecture, and then a little bit after the clay lecture, we'll have the banquet here. All right. See you all at the poster session. Wow.